So for an example of sketching curves using calculus, I have for us the following function. It is f of x is equal to x times x minus 8 cubed. So I'm going to try to run through the same 8-step process as what I ran through in the previous video. Step 1 is to analyze the domain of the function. You'll notice that f is polynomial. You see nothing but products of powers of x. Polynomial. I should probably know how to spell that, shouldn't I? Polynomials never have domain issues, therefore the domain is going to be all real numbers. For step 2 is discovering any intercepts this has. Now we've had the good fortune of putting this in factored form already, so if you want to have a really bad time, go ahead and expand that thing completely. Otherwise, you can just say that x times x minus 8 quantity cubed is equal to 0. Using a little bit of the parlance from pre-calculus, we would say that x equals 0 has a multiplicity of 1, and x equals 8 has a multiplicity of 3. Now, multiplicity is simply referring to the exponents associated with the factors that produce these x-intercepts. Now, when you have an odd multiplicity, the graph is going to cross the x-axis at those points. Multiplicity of 1 means it's going to cross through locally like a line, and multiplicity 3 means that it's going to pass through like a cubic. More on that after we actually do some calculus. No, not 3. The thing that comes after this, the y-intercept. For the y-intercept, we simply plug in x equals 0. We get 0 times. I don't really care what's after that, because 0 times anything is going to be 0, which we kind of already got from up here with the x-intercept of 0. Now, we'll go on to step 3. Step 3 is for symmetry, where we evaluate f of negative x and see if we get the original problem, the original function or the negative of the original function. So this would be negative x times negative x minus 8 quantity cubed. Now, if I were to factor a negative 1 from the negative x, negative 1 times x, I could also factor a negative 1 cubed from this term, and it would become x plus 8 cubed. Now, negative 1 times negative 1 times negative 1 times negative 1 is positive 1, so we wind up with x times x plus 8 quantity cubed. This is neither the original function, nor is it the negative of the original function, which means that we can conclude that this thing has no symmetry. For number 4. Number 4 was for periodicity, which does not apply here. Periodicity only applies to trigonometric functions for now, so we're going to go ahead and skip that. Number 5 is asymptotes. Asymptotes apply to rational functions, trigonometric functions, inverse trigonometric functions, exponential functions, logarithmic functions. You'll notice in there, nowhere did I say a polynomial function, so that also does not apply. Now let's get into the good stuff. The good stuff is going to come in the form of doing some calculus. Now, as I mentioned a moment ago, if you want to have a really terrible time with this, then I recommend expanding this thing completely. What we're going to do instead is take a derivative using the product rule. The product rule states this will be the first function times the derivative of the second function. Chain rule says multiply by the derivative of the inside, plus the second function times the derivative of the first function. First function being x, its derivative is 1. Now, a big advantage that we get here is we can factor out an x minus 8 quantity squared from both of these. If I take out an x minus 8, then for the first term, we'd be left with an x times 3 times 1. X times 3 times 1 is 3x. For this guy right here, we would be left with one additional factor of x minus 8. Combining like terms, we get x minus 8 squared times 4x minus 8. And factoring out that greatest common factor of 4, that'll be 4 times x minus 2 times x minus 8 quantity squared. The critical points are where this thing is going to be equal to 0. We'll refer to these as critical values. I set the first derivative equal to 0. It's a polynomial function, so we don't need to worry about this thing not existing. And we would get critical values at x equals 2, as well as x equals positive 8. Now, I know that those are my critical values. To turn them into critical points, I am going to head back to the original function and plug them in. So f of 2, we would get 2 times 2 minus 8, quantity cubed. That is 2 times negative 6 cubed. That's going to be negative 432. For f of 8, we're going to have 0 times 8 minus 8, quantity cubed. I'm feeling a 0 on that one. So 2 comma negative 432 and 8 comma 0. Haha! I fixed it. Turned my 0 into an 8. Now with that in mind, we have our critical points. We're going to use those as endpoints for test intervals to figure out our intervals of increase and decrease. So the endpoints were positive 2 and positive 8, which means that we're going to have a total of 3 test intervals. For negative infinity to 2, I am going to plug in x equals 0. And I'm also going to recopy down what that first derivative was equal to so that we know what we're plugging this into. So what we got from the previous page was 4 times x minus 2 times x minus 8, quantity squared. I'm going to plug in x equals 0. I get that f prime of 0 is equal to 4 times 0 minus 2 will be negative 2, and 0 minus 8 will be negative 8 squared. What I'm seeing here is a positive times a negative squared. Positive times negative times positive. That is going to be less than 0. That lets me know that this is an interval of decrease. Next up, for 2 to 8, I'm going to pick any number in there. We'll go with x equals 4. I plug x equals 4 into the first derivative. F prime of, that's not how you spell 4, there we go. F prime of 4 is equal to 4 times 4 minus 2, and then 4 minus 8, quantity squared. That is positive, and once we square the negative 4, that'll be positive. That is greater than 0. This is an interval of increase. Not too shabby. And finally, 8 to infinity, I'm going to plug in x equals 10. Nice round number. So, plugging this in up here, this will be 4 times 10 minus 2 times 10 minus 8, quantity squared. I see nothing but positive in there. So this is going to be another interval of increase. At this point, I can also apply the first derivative test to classify these as local maxima or local minima. So at 2, we're changing from decreasing to increasing. So the point 2 comma negative 432, which we got from the previous page, is a local minimum. We're going to find out before too long that it's also an absolute minimum, but that's not what we're here to do. At x equals 8, the function goes from increasing to increasing, which means that this critical point is neither a local maximum nor a local minimum. We'll describe what's going on with the graph before too long. Alright, next up, and I've already forgotten what number we're on, that was number 7, classifying as local maxima and local minima, and finally, number 8. This is where we figure out what's going on with the concavity. So I'm going to recopy the first derivative, and we're going to figure out a second derivative. Like we did for the first derivative, I'd like to make use of the product rule. I'm going to leave the 4 off because 4 is simply a constant multiple. So this would be first times the derivative of the second, 2 times this thing to the first power, times the derivative of the inside, plus the second times the derivative of x minus 2, that'll be 1. We're going to do that same trick that we used for the first derivative as far as cool algebra is concerned. We're going to go ahead and factor out an x minus 8 from both of these. When I factor it from the first guy, I'll be left with a 1 times 2 times x minus 2, so 2 times x minus 2, plus, when I factor out an x minus 8 from x minus 8 quantity squared, I'm left with x minus 8. Oh boy, more parentheses. All right, continuing to simplify, this will be 4 times x minus 8 times, oh boy, distribute the 2, 2x minus 4 plus x minus 8. Let's keep going. 4 times x minus 8 times. Combining all the like terms in here, we get 3x minus 12. There's a greatest common factor of 3 we can pull out of there. 3 and 4 will give us 12. And we are left with factors of x minus 8 and x minus 4. This tells me that the second derivative is going to be equal to 0 if x is either equal to 4 or 8. So for intervals of concavity, we would be looking at negative infinity to 4. I'm going to space these out a little bit better this time. 4 to 8, as well as 8 to infinity. So for negative infinity to 4, let's plug in x equals 0, and we'll plug that into the factored version of the second derivative. This will be 12 times negative 8 times negative 4. That is positive times negative times negative. That is going to wind up being positive. On this interval, our concavity is going to be concave up. For 4 to 8, let's use x equals 6. That's in there. So f double prime of 6 is going to be 12 times 6 minus 8 times 6 minus 4. That'll be 2. That is positive times negative times positive. Overall result is negative. On this interval, we are going to be concave down. And finally, for 8 to infinity, we used 10 last time. We can reuse it here. F double prime of 10 is going to be equal to 12 times 10 minus 8 times 10 minus 4. I'm seeing nothing but positive around here, so positive result means that this will be concave up. So what I'm going to do is take all of our intercepts, critical numbers, all that good stuff, and sort of organize the data at the top of the next page. If you need to refer back in the video to see where any of these numbers are coming from, please feel free to do so. What I'm going to do is create a nice long x-axis. 0 was an x-intercept. 2 was a critical point. 4 was an inflection point. 6 is absolutely nothing, but we're going to mark it off anyway so that we can get ourselves to 8 as well. So on the top side, I'm going to put f prime. On the bottom side, I'm going to put f double prime. So for f prime, we got that negative infinity to 2 was an interval of decrease. Then then we got a critical point at 2. From 2 to 8, it was increasing with a critical point at 8, so derivative was 0, and then it started being increasing again. So what happens on a graph with something like that is usually it winds up doing a thing that we refer to in pre-calculus as flattening out at that point. So that's where the slope of the tangent line essentially becomes 0, and then it goes in the same direction once again. For the second derivative, the intervals of concavity, we started off concave up from negative infinity all the way up to positive 4, where it became 0, followed by concave down on the interval from 4 to 8, at which point it became concave up once again. I'm going to see if I can put all of these things together. Now, something I neglected to do on the previous page that I should probably do now is for our inflection point. Now that we've verified that the concavity actually changes, we need a y value associated with 4. So heading all the way back to the original function, this is going to be 4 times 4 minus 8, quantity cubed, and a calculator lets us know that that's negative 256. So I'm going to take all of this relevant information and see if I can turn it into an actual graph. My y-scale, I'm going to go by hundreds at a time. So 100, negative 200, negative 300, negative 400, and a little more. We'll make sure it goes all the way down to negative 500. Negative 500. My y-scale, I'm going to go up by 2 at a time, just like we did earlier. So 2, 4, 6, 8, and I believe that was all of the really important stuff. Starting with intercepts. We had an intercept at 0, 0. You know what? I'm going to change the color up so that the color doesn't interfere with the axes at all. Let's go purple. Albion College, go Brits. So 0, 0, 8, 0 were our two x-intercepts. For critical points, we had a local minimum at 2, negative 432. That should be right about in that range right there. We had an inflection point at 4, negative 256, so about halfway in between negative 200 and negative 300. We'll see an inflection point. Negative 256. Then that came over to 8. So here is the good stuff. We want to draw a graph that passes through these 4 points with all of these appropriate increasing, decreasing, and whatnot. I guess we'll work our way from left to right. To the left of 2, we're supposed to see decreasing and concave up. So we're going to see it essentially flatten out for a critical point right here, and then start to increase very rapidly as we go to the left. In between 2 and 4, we are supposed to be increasing and concave up. Increasing and concave up is going to look just like this. As soon as we hit this point, it changes to increasing but concave down until we flatten out right at x equals 8. So we'll flatten out right at x equals 8. That is increasing and concave down. Then at 8, we change back to increasing and concave up. So we should see something that looks approximately like this. Now what I'm going to do is graph this in the graphing calculator using an appropriate window and see if we wind up with all of the same delightful looking details as what we did here. So we are going to graph. The function was x times x minus 8 to the third power. Math followed by 3 will get us a third power. I'm also going to set the window so that I can see all the same stuff here in the calculator as what we just made here. Oh yeah, we're going to need to fix that a little bit. Let's go from negative 2 all the way up to positive 10 in the x direction. And in the y direction, we went all the way down to negative 500. And we don't need to see a whole lot above the axis, so let's just go up to 100 for that. I'm also going to change the y-scale to 50 so that the marks aren't too incriminating. Here's the part where you cross your fingers really good and just hope against all hope that what you came up with just looks that good. You know what? Not going to lie. I'm pretty proud of myself for that one. Looks like it should have gotten a little bit flatter near x equals 8, but you know what? I'm not going to hold it against myself. We did well. We did pretty well. Cool. So that one example took nearly 20 minutes. So if you're finding that these problems are taking you a lot of time, that's natural. So please be patient, take your time, and do good work.